But this presents a paradox. If oxidation is always at the anode, the charge designation should not flip from negative to positive simply because the battery is plugged into a wall. Relying on memorized positive and negative signs fails when analyzing complex, reversible electrochemical systems. To master these circuits, we must look past static signs and track the thermodynamic trajectory of the electrons. We start with the universal physical rules. An electrode is the conductive interface where electrons leave or enter a chemical system. The anode is defined as the site of oxidation. It is where electrons are liberated from the chemical species. The cathode is the site of reduction, where electrons are gained by the chemical species. This creates an unbreakable physical law. Electrons always flow through the wire from the anode to the cathode. Physics tracks current, labeled with an I, as the flow of positive charge. Consequently, this theoretical current moves in the opposite direction of the actual electrons. These mechanics remain constant whether the battery is spontaneously discharging or forcibly charging. The Daniell cell is the archetype of a spontaneous galvanic system used to generate power. Its architecture requires the separation of half reactions to prevent a useless short circuit. The zinc half cell has a natural thermodynamic tendency to oxidize and release electrons. The copper half cell has a natural tendency to reduce, pulling those electrons towards its electrode. Because this transfer is spontaneous, the Gibbs free energy is negative. The zinc anode sheds electrons into the wire without any external push. As the source of this natural electron release, the zinc anode is designated as the negative pole. Without intervention, a counter voltage of built-up charge would instantly halt the flow. A salt bridge dissipates this charge gradient by exchanging inert ions, keeping the circuit alive. A galvanic cell intercepts a spontaneous energy release to produce a positive electromotive force, naturally resulting in a negative anode. Industrial electrolytic cells, such as those used for molten sodium chloride, represent the opposite thermodynamic scenario. The goal is the forced reduction of sodium and forced oxidation of chloride. This fights natural tendencies, making the system thermodynamically unfavorable. An external power source provides the energy override. The positive terminal of this battery forcefully rips electrons away from the chloride ions. Because oxidation is occurring at this electrode, it is still defined as the anode. However, it is now designated positive, as the external battery's positive pole is dictating the electron draw. The anode flips to positive in an electrolytic cell because its behavior is dictated by an external voltage source, not its own spontaneous chemistry. This electron flow produces a tangible measurement of physical mass. Michael Faraday quantified these observations of electrolysis. He theorized that the amount of chemical change is directly proportional to the moles of electrons exchanged. The Faraday constant represents the electrical charge carried by a single mole of electrons. The electrode deposition equation allows us to track this mass transfer by measuring current over time. Measuring current over a duration of time counts the discrete electrons used to plate solid metal onto an electrode. Electric current is a quantifiable stream of chemical reactant that physically alters electrode mass. Consider a battery where both the anode and cathode are made of the exact same metal. Under standard conditions, the difference in reduction potentials is zero, and the electromotive force vanishes. This limitation only exists under standard equimolar conditions. The Nernst equation accounts for non-standard conditions, tracking voltage as concentrations deviate from equimolar levels. The reaction quotient, Q, represents the ratio of ionic concentrations between the two isolated compartments. A concentration gradient alone generates a measurable electrical voltage. Electrons spontaneously flow to dissipate this concentration gradient until equilibrium is reached. Voltage does not strictly require two different metallic identities. It requires a chemical gradient seeking equilibrium. This process can be observed without inorganic components. The cellular lipid bilayer is a biological concentration cell. The cell membrane acts as the non-conductive barrier separating different ion concentrations. Sodium, potassium, and chloride power the human nervous system. The unequal ratio of these ions establishes the resting membrane potential. This thermodynamic principle also drives the mitochondria. The mitochondria utilize folded inner membranes to carry out these electrochemical reactions. The proton motive force driving ATP synthesis is mathematically identical to the inorganic electromotive force in a concentration cell. Whether it is a lead-acid battery firing an engine or a neural membrane firing a human thought, voltage is the physical expression of thermodynamics seeking equilibrium.